So we've determined again, solution of the equation is this, having applied the inverse transformation before we got the values of a, b, and c. And the values of a, b, and c are determined by partial fraction decomposition of this expression that we got from the Laplace transform of the original differential equation. Well, we've got to solve this for a, b, and c. So we put this over common denominator, which is s plus 4 times s squared plus 25, and then we compare numerators. We're going to get a times s squared plus 25 plus bs times s squared plus 25 and it's not s squared plus 25, it's s plus 4. I didn't like that cubic in the first place, which is what tipped me off to the fact that I was writing what I'd written before without thinking. So it's this over s plus 4 times s squared plus 25, and that has to equal 2s squared plus 50 over s plus 4 times s squared plus 25. So we get three simultaneous equations. The multiple of s squared has to be 2s squared. The s squareds that we get here are the a and then a b. So we have, and I'm skipping steps, review partial fractions if necessary, straightforward, but we get I'm writing down a little more than I absolutely have to, but the s squareds that we get are here and here, a plus as squared and a bs squared. That's what we have to give us the 2s squared. Then our multiples of s add up to 0. And what are multiples of s? Well, we get 4b times s and a c times s. So already we know that b has to equal negative 1/4 of c, or c equals negative 4b, either way. Then we have a times 25 plus c times 4 plus, not 4, equals 50. And if I've written that down correctly, let's double check it. I get a 25a here. I don't have a constant multiple of b, and I have 4c. So there we have it. And that's got to equal our constant term. Okay. The rest of it I think I've got right. Well, that's three equations we can easily solve for a and b. So we have a plus b equals 2, 4b plus c equals 0, and 25a plus 4c equals 50. This equation tells us that c equals negative 4b, so we have a plus b equals 2. There's no c here to replace. Replacing c here by negative 4b, we have 25a minus 16c equals 50. And, yeah, check me out on this. You could also write this as an augmented matrix and reduce it. Or write it as a matrix equation and solve it by inverting the matrix. You can do any of those things, and you can do them easily with software. So you translate this into whatever your software would process most easily. If you're using MATLAB, you probably use, I don't know, I don't use MATLAB, but you probably use an inverse matrix. In any case, this is what we get. And now just solving it by hand in one method or another. This tells us that a equals 2 minus b. So now we have 25 times 2 minus b minus 16. The 16c should be 16b. Since c equals negative 4b. And now we can easily solve for b. We've got negative 16b and negative 25b, so we've got negative 41b equals 25 times 2 is 0. Uh-oh, we're in trouble. Well, maybe not. Well, this would mean b is 0 and c is 0. And that's troublesome as heck. Write down the matrix, calculate the determinant, see if I did that right. A equals 2 minus b, 25a. How did that happen? We're going to end up with a equals 2. Actually, that works. Okay, well, it's a little simpler than I kind of wanted it to be, but I don't know if I just coincidentally wrote down a really ridiculous equation or not. This would then give us solution, just plain old 2e to the negative 2t. I know that can't be right because it doesn't give us the non-homogeneous part. It is a solution to the original equation, so again, I've done something silly with my algebra. It's all pretty straightforward, but I can't say I'm surprised. You're going to have non-zero multiples of the sine and the cosine. There's no question about that. So tracing back, well, I'm not going to take the time to debug the solution, but we can see that the solution to this equation, if we've got A, B, and C, is going to give us something that's a plausible solution of our differential equation, which we know to have a non-homogeneous solution that's a multiple of e to the negative 4t. And some combination of cosine and sine of 5t. I want to look back at one thing, if I can find it. It's where I had the y of 0 equals 2, which is what's going to say a lot about these coefficients. So let's take a quick look at that. Yep, there it is. Okay. I mean, I do get a 2s squared plus 50 over here. I've also got a 10 here. So this 50 should have been 60. Well, let's go ahead and correct that. Let's see how this really works out. So that should be 60. I'd like to make this prettier, but so be it. And my 50 here should have been 60. It was too much of a coincidence that this multiplied out to this. And let's just correct the rest of them. That should be 60. That should be 60. So there's 60. There's 60. And there's 60. And now negative 41b is 10. Still not totally confident. But now I have at least a chance of getting the solution right. 41 over 60 is kind of a weird fraction. It doesn't make me totally comfortable, but it isn't that surprising. So we have b equals negative 10 over 41. And then c equals negative 4b that would be negative 40 over 41. And then a is 2 minus b. 2 is 82 over 41. So it's 90 over 41. Again, work it out and see if this works. But our solution now, and do I have room to actually write this out? This camera's kind of perched precariously, but let's go ahead and do this. And so now we can say that y equals (90e to the negative 4t over 91), and b cosine of 5t would be minus 10 cosine of 5t over 41. It's 41, not 91. And then it's going to be plus or minus sine of 40 sine of 5t over 41. We can plug that in to our equation, and we're actually out of time, so I'm going to not do that. But remember, our equation was y prime plus 4y equals 2. Was it the sine or cosine? Doggone it. Where's my equation? I can't even find my equation here. There it is, it's cosine. Well, if we take these derivatives, set everything equal, the y prime is going to give us a negative 360 in front of e to the negative 4t. And of course our y is going to have a 360, so that's our solution to the homogeneous equation. That automatically works. So we just have to check whether 4 times this is equal to this, and it's close but not quite. This adds up to 50, that adds up to 200 over 41. It's not actually all that close. Okay, well, there's still some flaws in the arithmetic, but the process is very simple. So you just run through it a couple of times and you get used to it. And the thing that it should impress you about this is that we've taken this equation, we've transformed it by the Laplace transform, and we've obtained the Laplace transform of the solution, and then we inverse transform it, which involves partial fractions, which done carefully and correctly should lead us to a solution. The other part of this solution is that y of 0 should equal, what did we say, 2? Okay. And y of 0 is going to be 90 over 41 minus 10 over 41, which is 80 over 41. If it was 82 over 41, it would satisfy the initial condition. So again, my problem probably goes back to something regarding the initial condition. And let that just be a demonstration of the idea that if you know where things fit into the equation and how they relate to the equation, it helps you debug a solution. Okay, so I'm going to leave it at that.